Hello everybody, in this lecture we will be solving 1999 IMO problem number 2. Here is a view of this problem. In the first part, part A, we are told that this inequality holds for all non-negative real numbers x, and we are to find the least constant real number c that would have that happen. And in the second part, we need to figure under what conditions equality will hold. So the inequality will hold as an equality. Before I begin, I would like to make two observations. The first one is that if all the xi's are equal to 0, then inequality holds automatically. Inequality holds, and there is pretty much nothing to do, and as a result what I can focus my attention on only still on all non-negative real numbers xi, such that the sum of the xi's is greater than 0. So for the rest of the discussion, let's assume that that's the case. But then we can even do more than that. Upon observing that both the left-hand side and the right-hand side of this inequality consists of functions which are both homogeneous of degree 4. So recall that a function f x1 xn, it's a multivariable function, is homogeneous. Okay, I don't know how to spell that word. Is homogeneous of degree 4 if this holds, right? So, sorry for that. tx1 txn is equal to t to the power 4 f of x1 xn, right? Obviously, you can replace the 4 with any number there, and that we will say that it's homogeneous of degree that number, whatever it is. But regardless, that's obviously true for both the left-hand side and the right-hand side expression in our situation. So what it means is that I can refine this thing from the first part, and I can simply assume without loss of generality, in fact, we can assume the sum of all the xi's be restricted to be equal to 1. So in a sense, I'm scaling it. And if I can find the c, and as a result, and find the c for this case, then that c will also hold for all the other non-negative real numbers xi as well, by simply scaling it by a factor t, right? So it makes sense. So so therefore, for the rest of the problem, we will make this assumption, but then as soon as we add this assumption, look at the right hand side. We can see this expression on the right hand side. As a result, our inequality, let's call it the star inequality, reduces to the following: the summation for 1 less than or equal to I, j less than or equal to n, xi, xj, xi squared plus xj squared less than or equal to, and remember this is a 1 to the 4th power, so it's just a c where, so we need to make sure and we understand this condition, I equals from 1 to n, and that's it. So this is the equivalent representation of this problem. So if I can find the c for this particular case, that c will also be the answer for this case as well, thanks to the homogeneous nature of the functions on both sides of the inequality. Okay, now in the second step, I want to have a good sense of the left-hand side. So the left-hand side, as I said earlier, it's a function, it's a multivariable function, and so let's investigate this function. So f of x1 xn, well, obviously this f is different than this, so this f was just a generic expression. Okay, but anyhow, let's just keep the same notation, I guess. So this thing, so this expression is therefore equal to, so I can just expand, let's start like this actually. So let's first expand this. So xi cubed xj, and we still have I is less than j here, obviously, plus I is still less than j, x xi xj cubed. But then what I can do is I can rename these, right? I can easily rename these indexes. So as a result, if I rename them, so I still keep the first one, for I less than j, I cubed xj plus, and then summation for I greater than j, right? We will have xj, right, xi cubed. So regardless, we have this anyways, right? So what it means is that, well, obviously you can you can test it out with a few variables. For instance, what I did is let me show you my earlier work. I tested it for four variables just to convince myself that that's actually true. And in fact, I found out, well, I convinced myself of what I'm the fact that each of these can be represented in the following fashion, right? So but you can do something similar for yourself. So therefore, going back to our problem, so we can easily show, so you can easily convince yourself that this is in fact equal to, so from I to n, x sub I cubed times the following, basically 1 minus xi. What I mean from here is that recall that the sum of all the xi's is equal to 1, so xi cubed will have all the coefficients greater than I in front of it, and also all the ones less than itself. So as a result, it will have everything except I, right? Except xi. So if you want, let me write it that way. So it's x1 plus all the way to x sub I minus 1 plus x sub I plus 1 all the way to x sub n, but that's simply equal to x sub I cubed, I equals from 1 to n, 1 minus x sub I. And finally, I will rewrite this in the following fashion, as you will see next. I will just factor inside the xi squared, so it will be xi squared minus xi cubed, I from 1 to n. Now I want to investigate the features of this function here, so let's open some space on the side. So I claim that the function f of x equals x squared minus x cubed is increasing in the following interval 0 to 1/2. In reality, this function is increasing from 0 to 2/3, but I just need this part, and it's well, okay, so therefore, what I mean by that is, let me define it. So therefore, if 0, x, y, and 1/2, they can be equal, then I claim that x squared minus x cubed will be less than or equal to y squared minus y cubed, and I leave it to you as an exercise to do it. As I said, if you want, one way to do it is you can take the derivative, and I mean, using calculus techniques, it's very easy to see that this function is increasing all the way from 0 to 2/3, but then you can use some algebraic stuff as well. Okay, so I will study the rest of the problem as two cases. So the first case, so case 1. In the first case, let's assume that all the xi's, for all I, xi be in the interval 0 to 1/2. Let all the xi's be in this interval. then this expression here, let's call it star expression, then star is equal to actually it is less than or equal to, I should say, star is less than or equal to summation xi, I equals from 1 to n, and then open the parentheses. So I will just replace the xi's with 1/2 inside, okay, like that, because I know my function is increasing all the way to 1/2, right? In this interval it's increasing, so it will be definitely less than or equal to this number here, which is equal to, it is a constant, so I can take it outside the summation sign, so it would be 1/4 minus 1/8, it would be 1/8, so moving it outside, so 1/8 summation xi, I equals from 1 to n, and that's simply equal to 1/8. Now, equality condition will be satisfied if each of these expressions, so equality holds if xi square minus xi cubed is in fact equal to, so this thing, which is actually 1/8, we calculated. So equality holds if each non-zero xi satisfy this thing, and that's only going to work in this interval, by the way. And in this interval, this expression is equal to 1/8 only when, so this would imply that all the non-zero xi's which are equal to 1/2, right? So all the non-zero xi's have to be equal to 1/2, but at the same time combining this with the fact that so this and the fact that all the xi's add up to 1 suggests that, so it would further imply that there's only one implication, that there is 2, so this will hold if and only if, actually, if and only if xi xi's equal 1/2 for exactly 2. Actually, let me write it in English. For exactly 2, so for 2 xi, right? For two of them. Yeah, it's kind of, and the others are 0. Yeah, that would do the first case. So the first case gives us the desired result. Now the second case, case 2, in the case 2, we wonder what happens if at least one of the ai's, if for one of the i's, xi is strictly greater than 1/2. So in that case, let's assume that let's say that it is greater than 1/2 due to the symmetry of the problem for x1. Let's say that's the case, and let's see if in that case what happens, right? So the trick is the following. So all the other numbers, x2 all the way to xn, they are all less than 1/2, and what I will do is I will look at the sum of these numbers, and the sum of these numbers here, let's call it y is equal to x sub 2 plus all the way to x sub n, but that's simply equal to the whole sum, everything I from 1 to n, minus x1, or basically, because this is 1, so it is 1 minus x1. Now I will apply my result here, this result here, after I isolate the x1, because this result only holds in the interval 0 to 1/2. So after a small modification, so let's go back to our thing here. So therefore our function f of x1 all the way to xn, that's equal to, I'm just going to split it, right? So remember our function here, that's our function. I will split it. So the case I equals 1, I will take it out, and so it will become x1 cubed times 1 minus x1, and everything remaining I will keep the summation sign. I equals from 2 to n, x sub I cubed times 1 minus x sub I, and that's simply equal to and remember that we decided to call 1 minus x1 as y, so that's just x1 cube y plus and and let's factor inside xi as xi times xi square here, and then I'll take the xi square inside, so this is summation xi remaining here, xi square minus xi cubed equals from 2 to n. Now I know very well that if I replace these xi's, which each one is less than 1/2, with y, which is the largest value that it can take, they will all answer because of this increasing situation, monotonicity condition. Each of the x2, x3, all the way to xn are less than y as a result. So let me do it here. So therefore, this expression is less than or equal to x1 cubed y plus I equals from 2 to n xi times, and now I'm replacing these with y squared minus y cubed. And why? Because each of these xi's from 2 to n are each less than or equal, well, for each of these, because the xi's are less than or equal to y's, this expression will be less than or equal to this expression due to the thing. So for all I, let me write that down actually. So from 2 to n, we know that xi's are less than or equal to y, which implies xi squared minus xi cubed is less than or equal to y squared minus y cubed. Okay, so just to remind. Okay, now that's pretty good because this expression does not depend on I, so I can move it outside the summation sign. So that would simply be equal to x1 cubed y plus so I move it out, so it will become y squared minus y cubed, and then the summation here would be I equals from 2 to n xi. But wait, from 2 to n, the sum of xi's are simply equal to y. So therefore, finally, this simplifies to x1 cubed y plus, there's a y here, so that would give me y times a y squared minus y cubed. And sorry for that. And this is equal to, I claim, x1 cubed y plus actually I can factor out the y squared here, so I will get y cubed, and then 1 minus y. We earlier agreed that it's equal to x, because y is equal to 1 minus x1, so that's just y cubed minus x1. And I can further factor out the x1 y, and I will be left with this expression, which is not too hard to show that this thing is always less than 1/8 whenever x1 is greater than 1/2 and y is less than 1/2. For instance, one thing that you guys can do is, I will not show it here, but one idea is you can simply replace, for instance, x1 with 1 minus y, so you'll get 1 minus y times y, and then you'll have 1 minus y squared plus y squared, and you can you can factor out, let's see, well, obviously this part is less than, because y is less than 1/2, so this thing is definitely less than 1/4. Well, it's easy to see because this is just a parabola, right? So like that, and the greatest value will take place when it is 1/2, so this thing is 1/4. So this part is less than 1/4. So in a similar way, you can try to restrict and find a bound, or you can do it all together. Well, okay, so or you can even use calculus, I guess. Yeah, so that's therefore we can say that in this case, even in case 2, when one of the variables is greater than 1/2, the expression is again less than 1/8. So therefore, this gives us the solution, right? So combining case 1 and case 2, we can conclude that for x1, x2, and the solutions, the maximal value to our problem will be when exactly 2 of them is equal to 1/2, and the rest of them are equal to 0. So this will be the solution, that optimizes the function. And let me remind you the function again. Our function that we are optimizing now is this, so xi xj, xi squared plus xj squared, and here I is less than j, is now less than or equal to, we established that c must be 1/8, and equality condition holds when this is the case. So 1/8 is the maximal value that this function can take, and the equality condition will hold regardless of the values of xi, when exactly 2 of them are equal to each other, are equal to 1/2, and the rest is 0. And then now you might say, hey, but then how about the general problem? Well, the general problem wouldn't change, right? So we established earlier that because of our assumption here, simplifying assumption, I equals, due to the homogeneity of the thing, of this expression, we can now generalize it further and saying that in fact nothing would change if well, or basically what I'm trying to say is you can scale it, and as a result this solution is also the solution for the general problem, namely this one, right, that we started with at the beginning, so which is the claim, summation of xi's to the 4th power. I think that was the original problem, right? So and that's it, and we have solved, we have not only found the value c, but also we have established the equality condition by this given expression, and we are done. Let me remind you that in IOPS you can find alternative solutions to this. Actually, there's a troll solution using AMGM. You can solve this problem virtually in a few lines, so that's also very convenient as well. But hope to see you guys in our next video.